Welcome back to CognitionChunks. Yellowstone Day 7 Part 1. I failed to set the date correctly on my camera. August 28, 2022 was actually September 24, 2023, whoops. We set out from Canyon Hotel and headed west across the middle of the Figure 8 to Norris Geyser Basin for our first hike of the day. Norris Geyser Basin. Named by Philetus W. Norris, the second superintendent of Yellowstone, 1877 to 1882. Norris was instrumental in the development of early roads and facilities in the park. Emerald Spring. Named for its emerald green color. The green hue is due to the presence of yellow sulfur particles over a blue pool. A visually striking feature, but not unique in terms of geothermal activity. Steamboat Geyser, located in the Norris Geyser Basin of Yellowstone National Park in the United States, is the world's tallest currently active geyser. Its major eruptions can shoot water more than 300 feet into the air, although it also has smaller eruptions that are considerably less dramatic. Despite its incredible potential, the geyser is notably unpredictable, which makes its history quite fascinating. Chronological analysis of eruptions. Early documentation. 1878, steamboat was likely discovered in the late 1870s by early explorers of the Yellowstone area. 1879, first described in an account by the Hayden Geological Survey, which named it steamboat because its eruptions sounded like a steamboat's whistle. Inconsistent activity. Pre-1960s, there are scant records of steamboat's activity, but it was considered a dormant or infrequently erupting geyser for many years. 1961 to 1964, a period of more frequent activity, with eruptions recorded more consistently. Dormancy and revival. 1960s to 1980s, after the early 1960s, steamboat returned to an erratic eruption schedule. Several years of dormancy were common. 1990 to 2000, a few isolated eruptions occurred, but steamboat remained largely quiet. Recent resurgence. 2018-present, steamboat entered an unusually active phase, erupting as often as once a week in some months. In 2018 alone, it erupted 32 times, surpassing the previous record of 29 set in 1964. Influential factors and theories. Seismic activity. Yellowstone is an active seismic zone. Earthquakes in the region are considered to potentially affect the underground plumbing of geysers like steamboat. Geothermal energy shifts. Some researchers suggest that shifts in the geothermal gradient or energy supply may contribute to periods of increased or decreased activity. Human impact. Fortunately, there's no definitive evidence to suggest that human activity has significantly impacted steamboat geysers' behavior. Monitoring and scientific importance. Steamboat's recent activity has spurred renewed scientific interest in its workings. Researchers have deployed a variety of sensing equipment to better understand its eruption patterns and underlying mechanisms. Geological studies also often consider Steamboat Geyser as an example of a highly variable geyser, and its activity is sometimes compared with other geysers to understand broader geothermal phenomena. Cultural and social impact. Steamboat Geyser's unpredictable eruptions make it a symbol of nature's untamed beauty and power, drawing tourists, scientists, and media attention from around the world whenever it erupts. Understanding the history and factors influencing Steamboat Geyser can provide insights into broader geothermal systems, and it continues to be an important focal point for geological and hydrological research. Cistern Spring. Named because it acts as a cistern for Steamboat Geyser, emptying and refilling in relation to steamboat's activity. Its water level changes depending on the activity of nearby Steamboat Geyser. Significant for its interconnectedness with Steamboat Geyser. The ecology of extremophiles at Cistern Spring in Yellowstone National Park is a vivid demonstration of life's adaptability to harsh environments. Extremophiles are organisms that can survive and thrive in conditions that are detrimental to most life on Earth. Thermophiles typically live in temperatures ranging from 45 degrees Celsius to 80 degrees Celsius, while hyperthermophiles grow best above 80 degrees Celsius. Cistern Springs temperatures can exceed these ranges, offering a perfect niche for such organisms. Cistern springs' pH can vary widely, and accordingly, it can be home to acidophiles, which thrive in acidic conditions, and alkalophiles, which prefer basic environments. The pH of the spring influences which types of organisms dominate the microbial community at any given time. Chemolithoautotrophs derive their energy from inorganic compounds, such as sulfur or iron, found in their environment. This is opposed to photoautotrophs like plants, which use sunlight for energy. Extremophiles often form colorful microbial mats on the surfaces of springs. These mats are layered communities where different organisms occupy niches based on temperature, pH, and chemical gradients. The bright colors of these mats are due to the presence of pigmented bacteria, which can range from green and yellow to orange and red. These pigments often serve as protective mechanisms against intense UV radiation and as part of their energy-capturing processes. Extremophiles can also form biofilms, which are complex, slime-encased communities of microorganisms that adhere to surfaces. In hydrothermal features, biofilms provide a protective environment where extremophiles can share nutrients and genetic material, enhancing their ability to adapt to changing conditions. Echinus Geyser. Named by researchers from the U.S. Geological Survey. Named for the spiny, sea urchin-like deposits around its vent, Echinus is Latin for sea urchin. Known for its frequent and predictable eruptions, although it has been less active recently. The distribution of extremophiles' biogeographical patterns show clear biogeographical patterns that correlate with temperature, pH, and chemical composition of the water. This distribution offers valuable insights into how extremophile communities establish themselves and evolve. Studying these extremophiles provides a window into the potential for life on other planets and moons in our solar system, where conditions might be similarly extreme. For example, the thermal vents on the ocean floor of Jupiter's moon Europa might host life forms similar to those in Yellowstone's hot springs. Enzymes derived from extremophiles and have numerous applications in biotechnology. For example, Taq polymerase, an enzyme critical for the polymerase chain reaction, PCR, technique widely used in genetics, was originally sourced from thermophilic bacteria in hydrothermal springs. Black Pit. Named for its dark, murky appearance. A deep, dark pool with lesser geothermal activity. Heat source. The magma chamber beneath Yellowstone, estimated to be 5 to 15 kilometers deep, is the primary heat source driving the hydrothermal features. Water source. The extensive snow and rainfall in the Yellowstone area seep into the ground, where it is heated by the underlying magma. Plumbing system. Cracks, fissures, and porous rock formations provide pathways for the heated water to travel through. Depending on the pressure and the nature of the pathway, the water can manifest on the surface as geysers, hot springs, fumaroles, or mud pots. Surface features. When the superheated water reaches the surface, it results in the various hydrothermal displays for which Yellowstone is renowned. Crater Spring. Named for its crater-like appearance. A hot spring with a distinctive basin. Moderately significant but not unique. Key isotopes studied in geothermal systems. Hydrogen isotopes, deuterium and tritium compared to protium. The ratio of deuterium to protium in water can indicate the source of the water, meteoric versus magmatic, and the temperature history of the water-rock interactions. Oxygen isotopes, oxygen-18 to oxygen-16 ratios can reveal information about the temperature at which water-rock interactions occur and can also be used to distinguish between meteoric and magmatic water sources. Carbon isotopes, ratios of carbon-13 to carbon-12 in carbon dioxide can help determine whether the carbon in the gas comes from organic sources, biological decay or coal beds, from a mantle source, or from the dissolution of carbonate rocks. Sulfur isotopes, ratios of sulfur-34 to sulfur-32 in hydrogen sulfide can identify the source of sulfur, such as volcanic gases versus sedimentary sulfates. Helium isotopes, the ratio of helium-3 to helium-4 is particularly significant. A higher ratio of helium-3, a primordial isotope not produced in significant quantities on Earth, to helium-4, which is produced by radioactive decay in the Earth's crust, suggests a magmatic source and a connection to the mantle, which is richer in helium-3. Arch steam vent. Named for the arch-like structure from which it emits steam. Interesting as a vent, but not top-ranked in terms of geothermal activity. Mystic Spring. Possibly named for its enigmatic, misty appearance. A spring with frequent misty emissions. Thank you for joining us for another CognitionChunks episode. Please like and subscribe.